This is a question from digital communication in GATE 2020. In a digital communication system, four symbols S1, S2, S3 and S4 are transmitted. The symbol values are given. S1 is equal to -3, S2 is -1, S3 is +1 and S4 is +2. If the receiver receives it as Y is equal to S plus W, where S is the symbol and W is a zero mean unit variance Gaussian random variable. That is, S is a deterministic symbol given, Y is a random variable. If Pi is a conditional probability of symbol error for ML decoding, when S is equal to Si, then you are supposed to find the value of I for which the conditional symbol probability of error is the highest. Okay, the symbols are S, which can take values -3, -1, +1 and +2, and the symbols are given index. This is S1 and this is S3. Now these are the symbols that are transmitted at the transmitter side. This is the block diagram. S is what is being transmitted and a random variable is added that is equivalent to noise, W, and whatever is received is Y, and Y is decoded at the receiver. Since there is noise added, Y is prone to error. So you are supposed to calculate the probability of error for the different symbols that is being transmitted. Now that is, there will be Y received corresponding to S1, S2, S3 as well as S4. For every symbol that is being transmitted, there will be corresponding probability of error. I could index the probability of error as well. That is PE1, PE2 when S2 is transmitted, PE3 when S3 is transmitted, PE4 when S4 is transmitted. In fact, this symbol here is S4. Now, the question asks you to find that particular symbol which has the highest conditional probability of error. So, let's try to draw the PDF of the received symbol at the input of the receiver, at the input of the threshold detector. Normally the receiver probability of error is calculated at the input of the threshold detector. So let's try to draw the conditional PDFs at the input of the threshold detectors. The PDFs will again be Gaussian because the random variable that is being added to the symbols that are being transmitted is Gaussian. So we'll have four conditional PDFs. This is -3, this is -1, this is +1 and this is +2. This is what is being received. Received is Y. These are the possible values of Y. Now this is the conditional probability PDF of Y when S1 is being transmitted. This is the PDF of Y when S2 is being transmitted, Fy when S3 is being transmitted, and Fy when S4 is being transmitted. Now, if you observe, how is probability of error being calculated? Or according to the concept of probability of error, at the threshold detector, there will be always a decision boundary. Let me call this as decision boundary 1. Now, let's say consider when S1 is being transmitted, if the symbol happens to go beyond the decision boundary. Now, for this particular case, for example, when S1 is being transmitted and supposedly this is the decision boundary, When S1 goes beyond this decision boundary, it will be decoded as S2. That is, when you say S1 is decoded as S2 will be equivalent to an error for symbol S1. Similarly, there will be a decision boundary between the symbols -1 and +1. Between the symbols -1 and +1, there will be a decision boundary, and that I'll map it as decision boundary 2. Similarly, between +1 and +2, I'll have a decision boundary. Let me call it as decision boundary 3. Now, if you observe, I would say the probability of error for the symbols -3 and +2 is the least among all these 4 symbols. The probability of error for -3 and +2. Why? Because -3 can be decoded as an error only if it bypasses this decision boundary. That is, the symbol -3 is bounded by only one decision boundary. Same case with the symbol +2. The symbol +2 is also bounded by only one decision boundary. If it bypasses this decision boundary, the symbol +2 will be decoded as an error. So, however, that means I just write down this point. The symbols S1 and S4 are bounded by only one decision boundary. However, now take into account the cases of -1 and +1. -1 and +1 are bounded by two decision boundaries. For example, -1 is bounded by this decision boundary as well as decision boundary 2. Similarly, +1 is bounded by decision boundary 2 as well as decision boundary 3. That means it is more prone to error because in LHS it is bounded by decision boundary 1, in RHS it is bounded by decision boundary 2. However, the earlier case, in case of S1 is bounded by decision boundary in only one direction. This side is totally free. It is totally non-prone to error in this direction. But for -1 and +1, it is bounded by two decision boundaries. That is, S2 and S3 are bounded by two decision boundaries. Therefore, I could say probability of error for S2 and S3 will be higher compared to S1 and S4, or probability of error for S1 and probability of error for S4 will always be less than probability of error for S2 and probability of error for S3. That means since the highest probability of error is asked, I'll have to decide now between S2 and S3. Either of S2 or S3 will have the highest probability of error. Now, the second important point here is, now you can also, there is also another good concept in probability of error. Let's find out the distance between adjacent symbols in this particular problem. Let's try to find out the distance between adjacent symbols. Here, in this particular case, the distance is how many? This is -3 to -1 means 2 units is the distance here. Even here, you have 2 units distance. Even here, what you have is 1 unit distance. That is, for the symbol S3, let's consider the symbol S3, that is +1, that is being transmitted. Here it is bounded by two decision boundaries, but the distance between adjacent symbols are 2 unit here, 1 unit here. But for S2, the distance between adjacent boundaries are adjacent symbols are 2 unit and 2 unit. For S2, the distance between adjacent symbols are 2 units and 2 units. However, for S3, it is, it is 2 unit and 1 unit. So I'll just map it. For S2, the distances between adjacent symbols are 2 unit and 2 unit, and for S3 it is 2 unit and 1 unit. Now the important result is, the larger the distance between adjacent signaling points, larger the distance between adjacent signaling points, larger the distance, lower is the probability of error. That means larger the distance, I can say the distance is inversely proportional to probability of error. Larger the distance, lower is the probability of error. Now, if you observe, which combination has the largest distance? Largest distance among S2 and S3. Among S2 and S3, the largest distance between adjacent signaling points happens for S2. S2 has the largest distance between adjacent signaling points. Therefore, probability of error for S2 will be less than probability of error for S3. And in this question, which particular symbol has the largest probability of error is asked. We've already concluded that from this particular point, that compared to S1, S4, S2 and S3 has the highest probability of error. Now amongst S2 and S3, S3 has the highest probability of error. So the answer to this question is probability of error for S3 is the highest. And in fact, the question is asked in terms of index. The index would be I is equal to 3.